Today we talk about an important technical device which is used in circuits pretty reliably called batteries, and we'll talk about this weird word which I'm not going to even talk about right now. Capacitors are one way to create current, but they're often impractical. The rate of discharge is not constant, and it's usually kind of awkward to find, and they generally run down pretty quickly. Much more practical is the battery, a device that uses chemistry to create and maintain a constant potential between its terminals. The details of real batteries involve real chemistry, which is kind of annoying, and we're physicists, so we won't bother with that. Instead, we're going to use the conceptual model which your book calls the charge escalator. Here we see our battery connected by some wire and some other stuff maybe. We call these two things terminals, the positive and negative terminals. This is where positive charge sort of hangs out and we connect the wire is able to move. This is where negative charge hangs out. If negative charges are moving, we would do this, or it's where positive charges want to go. And then the idea is that there's some process going on that takes the positive charge, right? Positive charge comes here. There's a potential difference between here and here. It can't move across the battery, but when we put the wire, there becomes a path that lets it move this way down towards lower potential. And then inside, there's a series of chemical reactions that lift it higher and higher in potential to restore it to that higher potential where it will then go around again. Right. In so doing, as it goes around, of course, it drives a current. We should be careful here that although we oriented this way to make it look nice, it's an escalator, blah, 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 we're not really talking about gravitational things, so there's no relevance to the up and down. We could be looking from above at a battery and having a circuit go around like this or so on, but then the analogy breaks down and your book doesn't want to dwell on that. So we do have the idea that the charge escalator lifts a charge from low to high potential, the way that an escalator lifts a person from low gravitational potential to high gravitational potential. What we just drew was what's called a complete circuit, because charge can actually go all the way around the circuit and be reused. That's in contrast to an open circuit where, for instance, you break the wire and now there's no conductive path, so the charge rapidly comes to rest. It can't move, so it doesn't. A battery consists of chemicals called electrolytes, and they're sandwiched between things called electrodes, which are things that we call terminals there. Right? The electrodes are made of different metals. Some chemistry goes on in the electrolytes that causes charge to move so as to separate the positive and negative charges, but this consumes energy, which is why batteries will run down eventually. For some batteries, you can force current the other way. You can push current into the battery, into the positive contact. How would you do that? Well, for instance, if we took this, but then we stacked two batteries, and we connected them with a wire, and then with a wire, these batteries push harder this way than this one is pushing this way, and so current would flow this way through the battery. And for certain batteries, what that would end up doing is reversing the chemical reactions and restoring energy to the battery, storing more energy back in the battery. But for other batteries, what that would do is cause the battery heat up and explode. So you should probably not do that unless you're sure it's rechargeable. The chemical reactions create a potential difference, delta V battery, between the two terminals. For devices that can actively separate charges, we name this potential difference, this special thing, something called the EMF, pronounced exactly as it sounds, EMF. It's not pronounced EMF. You would think it would be, but it's not. EMF, which we symbolize by this symbol, which is sort of a curly E, or on the internet people say it's a capital epsilon, it's a magnified epsilon, which might be true. It's this weird curly symbol. And actually didn't mention here, but you can tell, since it is a potential difference, it's measured in volts. Because it is a potential difference. Why is it called EMF, which is sort of a weird name? Because Faraday, among others, used to call this thing electromotive force. And you can see that, again, here we have our EMF. But of course, it's not a force. The force is a thing that causes acceleration and affects inertia. This is what we now call a potential. Potential is not forces. And physicists grew increasingly embarrassed by calling thing a force that isn't really a force. So now we just hide that by using the initialism. Potential difference and EMF are almost the same thing. EMF is basically a potential difference. The distinction is that we use EMF only when we're talking about a thing which can generate its own potential, so which can actually force charges to be separated. Later on, we'll talk about potential differences, for instance, across the wire as the charge flows, and that's fine, but we wouldn't call that an EMF because the wire is not causing separation, it's just allowing charge to move through it. We ourselves will use this almost exclusively in the context of batteries. If we consider this arrangement here, batteries that are connected one after the other, like a stack like this, are said to be in series. These batteries are connected in series. If we take a positive charge and we put it down at the bottom here somehow, it must move through one battery and then the other and then the third. There are no options for where it goes. It always goes from here through here up to here. And when there's only one path that a charge carrier can take, then we say those elements are in series. The idea of series is going to come back over and over again. You might wonder what the other thing might be. Well, you might have a battery like this with a negative here and a positive here. And then another battery like this. And then you might take your wires and split them. Actually, we'll find out this is not a good idea, but you could imagine doing that. And here now, a charge particle, a charge carrier, getting to this part has a choice of going either up or down to one of the battery or the other. So these two batteries are not in series. They would, in fact, be, as drawn, the thing that's marked here, they're in parallel. And we'll use parallel a lot coming back and forth. We'll have parallel resistors and parallel capacitors and series resistors and series capacitors and so on. And it will always come back to, is there one path or two paths for a charge carrier to take as it goes through your circuit. All right, so here we have a battery and it produces a current in a wire. This is sort of the version of this thing. As the current continues, which of the following quantities decreases? And here we'll assume these are ideal batteries with ideal wires. Does the positive charge in the battery decrease, the EMF of the battery decrease, or the chemical energy in the battery decrease? It's going to turn out that it is only C. All right, it is only the chemical energy in the battery that decreases if they're ideal. Why doesn't the positive charge in the battery decrease? Because for every positive charge that is pushed through the wire here, another one is pushed onto the terminal. Otherwise, we'd be creating or destroying charge. How about the EMF of the battery? Well, that's controlled by the chemical reactions, and as long as those chemical reactions can occur, they'll create the EMF, so that's constant. But of course, as we push the charge through the wire and we give it some kinetic energy, that's got to come from somewhere, and it comes from the chemical energy of the battery.